Hey everyone, let's look at a slightly more involved trig substitution problem. Right, here I say in the notes, certain problems are a little more involved. In the following case, the necessary substitution is not immediately apparent. Right, because if we look, we notice, well, we don't have t squared minus a squared or something like that. Right, it's not even clear that we should be using a trig sub, except maybe that we've got a square root and we've got a quadratic inside. What we need to notice is that there is a perfect square added to another perfect square buried within that radical. We just need to flesh it out. So just note that this integral right here is the same thing as this. Watch me complete the square. Recall that completing the square means taking b, which in this case is -6, dividing it by 2, and then squaring it. Right? That's sort of what we're going to add to the end. That's what we want to have on the end to complete the square. So I'm going to write this in red to let you know that that's what I'm doing. I'm completing the square, right? -6 divided by 2 is -3, plus, squared equals 9, right? So it's plus. So it's plus 9, right? And then I guess we've got an extra plus 4, right? Just because plus 13 broke down into plus 9 plus 14. Okay? Well, that's kind of nice because then we can rewrite it like this. T squared minus 6t plus 9 is actually just t minus 3 quantity squared. And now you might notice we have the square root of something squared plus something else squared, right? Plus 2 squared. The problem with this is that, I don't know, it's a little bit different from what we're used to. We can make the trig substitution as before, but with something a little bit different. So here, watch this. We're going to let... I'm just going to write it up here just to conserve space. We're going to let t minus 3 equal 2 tangent of theta, right? Because that's the substitution, right? If this were an x squared plus 4, then we'd say, oh yeah, we've got to make it a tangent, right? Well, instead of that, it's just t minus 3, okay? Well, that means, of course, that dt is going to equal 2 secant squared of theta d theta, okay? So a little bit different, but it does work out. Okay? So what we're going to be left with is the following. Instead of dt on the top, we're going to get 2 secant squared of theta d theta. On the bottom, we're going to get the square root of, so is that instead of t minus 3 quantity squared, it's going to be 4 tan squared of theta plus 4. Let's see, I got that. Okay. And then this, of course, simplifies nicely, right? 2 secant squared of theta d theta all over 2 secant of theta, right? Because we're taking the square root of 4 secant squared. Of course, the 2's cancel out. The secants cancel out. And we're left with just the integral of secant of theta d theta. Kind of an ugly theta right there. Let's make it a little bit nicer. Right, there we go. Okay, so now at this point, remember this is what that weird integral, that weird u sub back at the end of integration by parts. So we're going to get ln of the absolute value of secant of theta plus tangent of theta plus c. And remember that at this point, we have to use our triangle, right? Create a little right triangle. Right? And here we're basing our triangle off the fact that t minus 3 equals 2 tangent of theta, okay? So what that means is that t minus 3 over 2 equals tangent of theta, right? Or tangent of theta equals t minus 3 over 2. right? So if that's theta right there, then we've got t minus 3 and 2. And then the hypotenuse, if you do it out, winds up giving us t squared minus 6t plus 13, right? If you do it all out, which again maybe should be expected since that's what we started with. Okay? So when we do this out, what's secant going to be? Well, I guess that's hypotenuse over adjacent all over adjacent plus, and then tangent of theta. That should be a little more straightforward because we, did that. And that's our answer. All right. So that's how we do this completing the square problem. Let's look at one more from today's lecture. Okay? Here we have a similar situation, except we really do need to add something on, but then of course we subtract because we can't really add any value. Right? So instead of saying note that, I'm going to say complete the square. We'll have that the integral of this guy, and by the way, there's a little typo here, right? That should have a dx at the end of it, right? This is the same as the integral of the square root of x squared plus 2x. Excuse me. Plus, now remember, we're going to complete the square, so we do 2 divided by 2 quantity squared, which is 1. But then, of course, we're not allowed to just add 1. We have to subtract it again. Okay? And then note that this is the same thing as the integral of the square root of x plus 1 quantity squared minus 1 dx. Right? So why is that useful? So now we can let x plus 1 equal, you see what it is? Secant of theta. And so it follows that dx is going to equal the derivative of secant of theta. Okay. So when we make the substitution, we're going to have that the integral of the square root of x plus 1 quantity squared minus 1 dx is really going to equal the integral of, let's see what we've got here. Square root of secant squared of theta minus 1 times dx, which remember is some extra baggage here. Okay? Now remember, you can simplify this and just skip this step if you want. I'm just doing it to, achieve maximum understanding, I hope, or promote maximum understanding. Anyway, we're going to wind up with secant of theta tangent squared of theta d theta. Let me actually just take a second to check this, because this is a bit of a, well, it's not terrible, but it's a little bit of a pain in the butt to do. I'm pretty sure we did everything correctly. So what that means, here you need to notice that this is really the same thing as secant of theta times secant squared of theta minus 1 d theta, and that's the integral of secant cubed of theta minus secant of theta d theta. And remember, we had special integrals for each of these terms, right? Secant cubed. In fact, they're both found in the same spot. Right, secant cubed. Whoops. Where are we over here? No. We're somewhere. I think we're here, perhaps? Nope. Oh no, you know where we are? It's not at the end of parts. Sorry, I lied. It's at the end of trig integrals. Here we are. Both integrals are right here. We know the integral of secant, right? We just did that one. The integral of secant cubed, right? Maybe we'll just borrow this bad boy for a second here. Just copy that. Maybe just paste it where appropriate. 1/2 of that. Maybe get rid of this plus c. And then plus, or I should say minus, ln of the absolute value of secant plus tangent plus c. Woof. Okay? And then I guess really we're not even quite done there because we need to get our triangle going, right? It's the thing with trig sub, right? Every time you think you're done, a little bit more involved. But this is really just kind of busy work at this point, right? We let x plus 1 equal secant of theta. Secant of theta is hypotenuse over adjacent. So we're going to wind up with this, right? Do the Pythagorean theorem, right? Take square root, okay? So then this is going to wind up equaling 1/2, and just have to do a little bit of plugging in, right? X plus 1 times tangent of x plus ln of the absolute value of, okay, well, we already had these guys, right? We're just seeing something with secants and tangents. You see them all over the place. Right, and then this is going to be minus ln of, I guess that's a closed parenthesis, minus ln of the absolute value of, this guy. Right, I guess if you want, you could just, really what you could just do is actually erase this and change this to a minus. Right? Because of this minus and this plus a half, right? Right, so you can do that if you wanted. And that's how you do that problem. So that's how you do completing the square. Remember, this will not be on your exam, but it is another chance to apply trig sub. Thanks for watching.